Hi everyone. In this question, we are given a binary tree which has standard left and right nodes plus a next pointer which is initialized to null. And what we have to do is we have to populate the next pointer to the node on the right for every level. If there's no node to the right of any particular node, the next node should be set to null. So what I mean to say is at every level, we have to see if there's a node to the right. If yes, we are going to set its next pointer to that particular node. If there's no other node available on the right, we are going to set it to null. So the thing here is that since this is a BFS playlist, we're going to solve this using BFS. So at every level, we are going to implement BFS using a queue in an iterative manner, and level by level, we are going to process the nodes and set the node to its right, set the node's next pointer to its right node. And we're going to process this level by level. And yeah, so let's code it out. So we're going to use the standard BFS. Let's see what the constraint says. So the constraint says that number of nodes can be 0 to 6,000. It means root can be null. So if my root is null, we need to do a sanity check. In that case, we return the root or null. Now next what we do, we have a queue of what do we store? We store nodes in that queue. And let's name this queue. Let's have a linked list implementation of the queue. Now, initially, we need to add root to the queue and process up until queue is not empty. So while queue dot is empty is false, we are going to process. So this is camel case, and this is standard BFS. In the end, we have to return root. And in this, what we do, we calculate the level size. The level size is given by q dot size. And then we have a current node current, which we poll. And but before that, we're going to, at this particular level, I know that I have level size number of nodes. So let's process those number of nodes using an iterator. So I is less than level size I plus plus. So whatever nodes I pull out during this iteration would belong to this level, right? So my node current would be equal to the node I pull out. So it would be q dot poll. We'll do some processing here. So I'll write that later. But in standard BFS, what do? We add its left and right child to the queue as well, right? So now we're going to add, if my current dot left is not null, we'll add it to the queue. The queue dot offer current dot left, and same with the right child. So this is how standard BFS works. Let's write offer here. But add would also work. Now we know one thing, that we have to connect current to the next node, right? On that particular level. How do we do that? So I know that there would be a next node to the right if my I is less than level size, correct? So if my I is less than level size, wait. So if I is equal to level size minus 1, it means that it is the last node of that particular level. So if I is less than this value, I know that there is a node to the right. So what I need to do? I need to set the next pointer of current to the next element at the Q, like the top element at Q, which will be given by peak. So this was the logic we used. And let's run this. Submitting this. So coming to the time and space complexity, in our case, our time complexity is big O of n. If n is the total number of nodes, we are adding it to the Q ones and we are pulling it out from the Q ones. So every node is processed exactly once. So that's why big O of n, and space complexity is big O of, so my time is big O of n, and space complexity is big O of, we can say if in terms of n we write it, we can write big O of n, or we can also write big O of 2 to the power h in terms of height, worst case. So any of this holds true. So why? I'll tell you the reason why. Let's say we have n as total number of nodes. So in a complete binary tree, what happens? My total number of nodes is equal to 2 to the power h plus 1 minus 1. We have these many number of nodes in our complete binary tree. So when we solve this equation, substituting, 2 to the power h, if we try to get it using n. So what happens then? My n plus 1 is equal to 2 to the power h plus 1, right? So if I do n plus 1 by 2, then it becomes roughly equal to, or let's say roughly equal to h. So n plus 1 by 2 is, can we write this like h is roughly equal to n by 2? So, and we ignore constants when we write big O of, when we write it in big O of, big O notation. So that's why I've written big O of n space, or we can also say big O of 2 to the power h. If like we have a complete binary tree, then let's say big O of w, if that is the maximum width of the tree, or let's say we can also write it in terms of n as big O of n, and at the last level we have 2 to the power h nodes. Because at every level, if h is the height of the tree, the number of nodes keeps incrementing by 2 to the power, by it. If it's a complete binary tree, it literally gets like here we have 2 to the power 0 nodes, here we'll have 2 to the power 1 nodes, here we'll have 2 to the power 2 nodes. So 2 to the power h is the number of nodes at any given h, which is height. So yeah, this was time and space complexity. Thanks for watching. Bye.